Good morning, good afternoon, and good evening to everyone who has joined the last webinar for the 2023, organized by the IOMP. And today's webinar is focused on early career. So the subject is early career in medical physics and the most recent trends in diagnostic imaging and radiotherapy. And with this, I have the pleasure to introduce today's moderator, Professor Kwan Hoong, who is the chair of the IOMP Awards and Honors Committee, and also professor at the University of Malaya, Kuala Lumpur, Malaysia. So without any further ado, Kwan, the floor is yours.
Thank you very much, Madalena. And good evening, good afternoon, and good day to all our colleagues, those who have tuned in to listen to this webinar. We have two excellent speakers. Let me introduce them to you first. These two are the awardees of the International Union of Pure and Applied Physics Early Career Scientists. The first one is Hong Chi Tan. He will speak on the impact of dispersive proton beam on reference dosimetry in a synchrotron spot scanning system. Now, he is currently a senior medical physicist at the National Cancer Center of Singapore, the NCCS. He's also a clinical instructor in the Duke NUS Medical School. He's received his PhD from the NUS and completed his residencies in NCCS. Also, by the way, he's also board certified by the IMPCB. He's active both in the radiotherapy research and education in Singapore, for which he was recognized with institutional level awards, and also recently the C4 Young Leader Award. And his current research interests are in the application of AI in radiotherapy, in adaptive radiotherapy, and proton therapy. Okay? And I'd like to introduce the second speaker. Is Dr. Choirul Anam from Indonesia. He will speak to us on the automated dose and image quality measurement from clinical CT images for CT optimization. And Choirul has his PhD from the Physics Department, Bandung Institute of Technology, the ITB. He also received his master degree from the University of Indonesia, UI, and a BSc from the Diponegoro University. And he's currently working as a lecturer and a researcher at the Diponegoro University. And his research interests are in medical image processing and dosimetry for diagnostic radiology, in particular in CT. And he's a prolific researcher, author, co-author over 200 papers. And in the last 10 years, he was the first author over 50 papers. And one of his papers published in the JACMP has been awarded as the best medical imaging physics article in 2016. He also received the Best Paper Award during the 15th CCOM. He was also recognized as an outstanding reviewer for the Physics in Medicine and Biology, the PMB, in 2018, and also for the Biomedical Physics and Engineering Express in 2019. He was also awarded as a CFOM Young Leader Award 2019.
Okay, great. Okay, thanks for introduction. And thanks for the invitation to give this talk. So this is the title of my presentation. So one moment. I have no conflict of interest to declare. And this is the content of my presentation. First, I will give a very brief introduction to the proton therapy facilities in National Cancer Center, Singapore. And then I will talk about our proton beam absolute dosimetry measurements and some of the issues that we encountered, and then which is in turn related to the next topic about measuring dispersion in the clinic. And lastly, I will just conclude and some point moving forward. So the way this talk is structured is in a very chronological manner. That means from from the time when we discovered the problem to the time where we found solutions and essentially also understand the physics behind the observation and the problem. So here's our NCCS proton therapy facilities. So we are Hitachi synchrotron systems. We have 4 full rotating gantries and 1 fixed beam room. And we started treating our first patient this year in June. And now at this point, we have treated over 70 patients. And all rooms are equipped with CBCT imaging, so we can do a very, very good IGRT. And we can also have a very good adaptive program as well. And then our system uses a discrete spot scanning system. So as shown in this schematic here, it means that there'll be pencil beams, and each pencil beam is scanned laterally across the tumor and also across the depth by varying the energy. So when the beam is scanning laterally, right, the scanning magnet X and Y, the current through it will be changing, and then to deflect the beams across the tumors. So during commissioning, we did a lot of measurements. So we did a mechanical, dosimetric, and imaging. And in this talk, we'll be focusing on the absolute dosimetry measurements. So absolute dosimetry measurements is actually in pencil beam scanning systems, it's actually done for each energy layers. And the idea essentially is just to get your gray per MU for each energy layers. So, and these absolute dosimetry measurements, the measurement condition is very similar to reference dosimetry. So in a PBS systems, it's important to emphasize that it's important to actually perform such absolute dosimetry or reference dosimetry with a monoenergetic beam rather than SOBP, because this is how the control system works at single energy levels. And current TRS-398 do not have reference dosimetry for PBS systems, but if anyone is interested, there's a draft of the revised TRS-398. It's not finalized, but there's a draft which will eventually contain the reference dosimetry condition for PBS systems. And then, as mentioned earlier, the TPS will actually requires this absolute dosimetry data to determine the protons per MU for each energies for Monte Carlo dose calculation. So this data is actually very, very important. I mean, firstly for your QA, but secondly as well to commission your beam models in your TPS. So this is a diagram of the reference condition for PBS or pencil beam scannings in the revised TRS-398. You can see here, depending on whether you are using a cylindrical ionization chamber or are you using parallel plate ionization chamber. So it's usually placed at the plateau region of your monoenergetic beams. And the patterns of the irradiation pattern is shown here. So it will be a rectangular grid of spots with certain spot spacing, delta X and delta Y. Usually they are the same. And the idea is to choose this spot spacing to be small enough such that you actually get a rather flat uniform dose. And then also the field size should be large enough to actually have to achieve a good lateral charge particle equilibrium. So the charge measured in this reference condition, right, can in fact be related to the dose error product using this formula. So I mean, for some of us that are more acquainted with TRS-398 will know all this terminology here. So MQ is a charge, NDW and KQQ not factors, and delta X delta Y is spot spacing, and this will give you the dose error product. And dose error product can in fact be related to the number of particles delivered per spot on the surface of the water phantom. So over here is a SERMA and here's a fluence at the surface. So from here, right, what we can see is by doing the reference dosimetry measurements, what you are checking in fact is the number of protons delivered per spots at the surface of the water phantom. So this measurement is supposed to be very, very simple with a water tank and with an ionization chamber placed at the plateau regions, typically 2 cm depth. And you should probably be done with these measurements in a day. But what we noticed was we have noticed a lot of high dose fluctuations when we do repeated measurements. You can see that there's quite a couple of energy layers with those fluctuations above 3% and above 5%. It's large. And the first question is, I mean, it's even more challenging than doing electron dosimetry. So something is not right here. So we try to figure out what's wrong. And yeah, so we try to figure out what's wrong. And this brings us on these investigative journeys. So first of all, we collected the log file for all this irradiation. The log file is collected from the spot profile monitor SPM and the dose monitor. And then we devised a very simple pencil beam algorithm to calculate the expected charge that is to be collected at the ionization chamber and compare the measured charge. The idea is that we want to see whether is this dose fluctuation, right, something that can be predicted entirely by the spot characteristics, like the spot position and the MU. And we do this as a function of different sizes ionization chamber, different spot sizes, which is equivalent to placing ionization at different depth, and also different proton energies. So we have a low energy, the lowest energy, the highest energy, as well as 182.7, which is one of the fluctuating energy. So just some more information about log file. So the log file contains the XY positions at the SPM, which is located here. So ISO center is here, SPM is here, and you have and on top you have the scanning medic. And then it also contains the spot width at the SPM because it's a multi-wire proportional chamber. And then you also have the MU recorded at the dose profile monitor, which is just after the SPM. And this shows a diagram of the different ionization chambers that we use. So idea is that they have different sensitive volume. So we have very, very small one, pinpoint 3D, to a very, very large one of diameter 15 centimeters. And there is also some information on the simple pencil beam algorithm that we have. So it seems a bit complicated, but the idea is that we just let each spot, right, assume a 2D Gaussian functions, and we just sum the dose of these energies within the sensitive volume. And the idea is that E ion, there is the integrated dose or charge within the sensitive volume should be proportional to the measured charge. So these are some of our results. So when we look at the lowest and highest energy, and this is the data from different ionization chambers, and we show that everything actually follow a linear relation, which shows that our simple pencil beam algorithm actually works well to predict the measured charge. And if we take a look at the relative difference of each measurements relative to their means, we can see that for these two energies, most of the fluctuation lies within 2%. So there's no issue with these two energies. But if we take a look at 182.7, which as we said earlier, is one of the fluctuating energy, we can see that those fluctuations actually range from from -6% to about 3% here. So it's actually 9% in this case. And another thing is also we also notice that if you are using a smaller ionization chamber like pinpoint 3D, the fluctuation is actually higher. And if you are using a very, very large ionization chamber, there's essentially no fluctuations. So this seems to give a hint that a lot of these things is actually, and what you can see here is also all the data point, right, actually pretty much lie along the line here, which means that we are able to predict for all these fluctuation. And it implies that this fluctuation seems to be originated from all the spot characteristics. And if you look at different depth measurements, at a deeper depth, the fluctuation drops. And this is because at a deeper depth, the spot size actually increases. And if you're at 2 centimeter depth or 6 centimeter depth, the fluctuation is actually still more than 6%, it's still large. But in one observation that we can find here is also that it's interesting that the fluctuating dose point, right, actually stratified itself into two different regions, the colder dose and the hotter dose. And this kind of and the question then for us is what happened to this? What causes this cold dose and what happened to this hot dose? So it's not like the data actually lies entirely along the line, but it stratified itself into these two regions, the colder and the hotter regions. And if we take a look at the spew change, which happens at for these cold measurements and for these hot measurements, we realize that very interestingly, all the circle here represent the spew change positions, and blue color represents the spew change for the cold dose measurement, and red color represents the spew change for the hot dose measurement. It's interesting that all the colder dose measurement actually happens just one column before the hot dose measurement. And if you take a look at the spot profile, spot position deviations from the log file, you can see that the spot position deviation is actually not constant, and it's not zero, it's certainly not zero, and it's not constant throughout the spill. In fact, it's drifting, it's increasing, or it's decreasing across the spill. And to explain and to show why this spot position deviation is the cause of this source fluctuation, I'll use this simple diagram to explain. So let's say you have two different spot position deviation profile. So in spill 1, the spot position increase in this manner, and in spill 2, the spot position also deviate in this manner. What happened here is, in this spill change region, there will be a region of hot dose. And the position of this spill change is not the same across all measurements. It's largely the same, but it's actually pretty erratic. It's actually difficult to predict. It's actually stochastic. So therefore, what it means is that for one irradiation, the spill change might happen here, and for the other irradiation, the spill change will happen probably one column before. And therefore, if your spill change happens very close to the sensitive volume of the ionization chamber, then depending on the precise location of this spill change, you might get hot and cold dose in the measurements. And that's actually the root cause of this. And that's actually the root cause of this fluctuation. It's due to spot position deviations and spill change happening very close to a sensitive volume. And we did a simple simulation here to look at the kind of percentage dose errors with respect to these spot position deviations. So up to 1 millimeter spot position errors, you can see that if you have a 0.25 cm spot spacing, which is what we are using now, and a 0.2 centimeters or 2 millimeters spot width, which is also the spot width of our highest energy proton beams, you can get those errors up to 7%. And if your spot size is actually larger, your dose error is smaller, and if your spot spacing is larger, you actually get a larger spot errors as well. So most of all these things are pretty intuitive. So after finding out the root cause of this problem, then the next question for us is, why does spot position deviation changes across the spill? So this should bring us to the topic of dispersion. So dispersion in accelerator physics lingo is, it's just steering errors due to different momentums. So when your extractor beam has different momentum, let's say the one in blue and the one in red, in this kind of situation, if there's a dispersion in your system, the dx, then it will lead to a delta x. It will lead to a spot position deviations. So of course, if your system does not have any dispersion, then no matter what's your errors in the momentum, there will not be any deviations, spot position deviations. Dispersion is typically created by a dipole magnets. So when you're bending magnets, you get all this dispersion. You start all this D function coming out, and you can do all those matrix and do the transport of the dispersion for dipole, for quadrupole, and so on. Ideally, in a synchrotron, the dispersion will only happen in typically in one plane, because the bending magnet will only bend in one plane. And as shown here with dispersion, what happened is it will actually blow up your spot size as well. And these are some of the for some of us that knows accelerator physics. The phase space can through a dipole, quadrupole, and all these magnets can actually be transported through the transfer matrix. And the dispersion can also be transported using a matrix. And in a dipole, it will change the dispersion and the dispersion gradient. But what's important is here in a drift space, if let's say a drift space is defined and there's no magnetic component, in a drift space, the dispersion is only transported linearly, which means the gradient will always remain the same, constant. And with this knowledge, right, we actually propose a way to measure a dispersion in the clinic. Because typically in an accelerator, it's actually very difficult to do dispersion measurement. Sometimes you have to tune your magnetic field, your magnets, or your RF to actually get the kind of deviations and to measure the spot position deviations. And all these things are actually not very easy to do in a clinical proton system. But over here, we propose a method to measure dispersion in a clinical system. So first of all, in proton therapy, the range of the proton can be related to the energy of proton using the Bragg-Kleeman relationship. And if you do say some simple algebra from here, and differentiation and so on, you notice that delta R, right, can in fact be related to a delta POP. which means that if there's a momentum errors in the proton beam, in the extracted proton beam, then it will translate to a range errors. And using this knowledge, if we can measure the range error throughout the spill, then we will have a way to measure the momentum errors. So at this stage, we have a way to measure delta POP. To get a dispersion, we need two parts. We need a delta POP and we also need a delta X. And to get delta X, we have two ways of doing so. First, the log file from the profile monitor and the SPM actually contains spot position deviation within the spill. So this by itself natively already gives us the delta X. And at the ISO center, we will put a scintillation detector to measure the spot position deviations. And with this, we will be able to measure 3 different spot position deviations in the PRM, SPM, and the ISO center. And then with the range measurements, with the range measurement or the delta R measurement, you will get the momentum errors. So with delta X and delta P, we will be able to get the dispersion across at PRM, SPM, and the ISO center. And as mentioned earlier, if this is a drift space, which it is, and because we are not using, there's no scanning, we're not the proton spot is only directed at the ISO center, then the dispersion at PRM, SPM, and ISO center should all lie along a straight line. And these are the instruments that we are using to measure the range drift and the spot position drift at the ISO center. So it's a SRE 4000, it's a scintillation detector, and then there's a mirror and there's also a CMOS camera. So, and then it actually has a nice accessory known as a Ranger 300. So this is actually an entire scintillation block, and it can do a time lapse. Proton range measurements, and yeah, and these are the two tools that we use. And these are set up, so we actually measured using the Ranger at gantry 90 degree and gantry 0 degree, and we also measure the spot position drift at gantry 90 degree and 0 degree. So we do a 0.2 second sampling time, and then to show that the Ranger that we have is actually suitable for measuring the range errors, we actually do these very simple measurements using plastic of about 50 microns. We show that the Ranger is able to detect a range difference of down to 0.1 millimeters. So the Ranger is certainly sensitive enough to measure the delta R. So these are some of our results. So at 168.0 MeV, you can see that the range across the spew actually slightly dropped across the spew, and it's actually kind of reproducible. Like, across all the different spews that we have, the range actually drops slightly. And when you go to gantry 90, the range, you also get a similar measurements. And if you look at the SPM and the PRM positional deviations, you can also see the drift in the positions. So in gantry 0 degree, the drift is in the X direction, whereas in gantry 90, the drift is in the Y direction. This is due to the precession of the phase space. And then when you do at 107 degrees, we can actually see a more prominent range drop across the spew for both gantry 0 and gantry 90 degree. And then for spot position measurements, the spot position at the ISO center is shown in the top plot for both these two figures. And from here you can see that sometimes the spot position deviation will actually go in the opposite direction to the spot position deviations in the SP and the PRM. The idea is because if the dispersion has a zero crossing between the SPM and the ISO center, then the spot drift will actually drift in opposite direction at the SPM and at the ISO center. So this is due to a zero crossing. And also we have very, very similar measurements as well in the spot position deviation. Okay, so with this data that we have, right, we actually get the dispersion at the PRM, SPM, and ISO, PRM, SPM, and ISO for both energies. Actually, we did for all the 9 energies, but I just showed these 2 energies just to show the idea. And you can see that indeed, right, these 3 points does lie along a straight line. And typically, there's no reason to expect that gantry 0 and gantry 90s, the dispersion profile should be the same, because the bending magnet, the current is actually tuned kind of differently based on the gantry angles in the Hitachi system. So everything's not entirely the same. And then if we take a look at the maximum range error that we have in these measurements, we can see that most of the range errors that we have is less than 0.3 millimeters. And from TG224, which is the equivalent of TG142 for photon QA. So TG224 is a QA report for the proton therapy, and the tolerance limit for the range errors is 1 millimeter in daily and monthly QA. So we are actually way within this tolerance limit. And the maximum delta POP that we register is everything is less than 0.08%. So this is good. And Hitachi promised us that the delta POP should be less than 0.2%. So we are way within the Hitachi limit as well. And this is a dispersion measure at the ISO center and also at the SPM. So in general, they are not the same across all the different gantry angles, and here's the dispersion gradient. Okay. So one good thing about this is, so after doing these measurements, at the very start, when during our commissioning, we found that the flatness of the beam is actually not good, as shown by the red color dots here. It's actually slightly less than 6%. So the flatness is not good. And when we do a dispersion measurement, which is shown by the magenta and the black line, the magnitude of the dispersion is pretty high. So when we show Hitachi this, you say, hey, can you tune the beam again and then get the dispersion down? And they did. So after tuning, we actually get the dispersion shown by the red and the blue line. And the magnitude is definitely lower. And what is clear is after tuning, the flatness of the beam also improved. Everything is better than 3%. So, I mean, for us, showing the dispersion measurement, all these things, does help in convincing the Hitachi engineer to do something about the tuning to get the dispersion down. So in the end, we get a better beam qualities and better treatment plan for the patients. So in conclusion, so we think that it's important to understand and quantify the dispersion system during commissioning. I mean, you don't have to do it as a QA, as a periodic QA. I mean, it's very time-consuming, but at least it should be understood first time during commissioning. And such tests are currently not covered by TG224. And as mentioned, the flatness can be a good surrogate QA, as shown here. So when at the start, when the beam is actually not very flat, when there's a dispersion and there's this spot position drift during the spill, we get spot profile like this. I mean, you get spot profile like this. It looks pretty bad. And you can use this to kind of gauge the intra-spill spot position deviations, but it's not a quantitative ways to measure dispersion, and also not quantitative way to measure spot position deviation as well. And then last point is the intra-spill spot drift is chances are it has a minimal clinical impact, because in realistic clinical treatments at the SOBP, the spot width is about 4 millimeters to 5 millimeters in water. So sigma. So with this spot width, right, if let's say you have 0.5 millimeter spot drift, it doesn't change the dose distribution much. So it has minimal clinical impact. And lastly, nonetheless, the main problem is that if you have dispersive beams and if induced those fluctuations during your absolute or reference oscillatory measurement, you could introduce a wrong input data into a TPS, and this will have a far-reaching consequence to the patients. So this is a part where we think that it's important to do this. That's why it's important to do this once during your commissioning. And the reference condition for the PBS in revised TRS 398 may not be feasible in this situation, because, as we mentioned, even with this rectangular spot grid, right, with these fluctuations, you cannot do a very reliable dosimetry. So, but again, there are still other promising way forward. So there are several research groups that show that it's possible to do those area product measurements using a large area ionization chambers. So there are a couple of work out there, and we think, and as shown here, it's possible. Ideally, using reciprocity theorems, these two conditions should be able to give very similar DAP measurements. And with Bragg chamber with a single spot, the good thing is that it's insensitive to any spot positional drift. And we think that this will be a promising step forwards to kind of overcome this problem. Yeah, that's the end of my presentation. And this,
thank you very much, Hong Chi. updated a lot about the importance of the dispersion. Is something equivalent to flatness for the photon beam, but it's much more complicated. Please send your question to Q&A if you have any on Hoong Chi's talk. Next, I'd like to listen to Dr. Choirul Anam. Choirul, now is your. Could you share screen?
Okay, thank you. Dr. Hoong,
Can you unshare?
can you close your screen first? Okay. Assalamualaikum warahmatullahi wabarakatuh. Good morning, good afternoon, good evening, everyone. My name is Choirul Anam from Indonesia, and now I will talk about the automated dose and image quality measurement from clinical CT image for CT optimization. This is my content, introduction. The second, patient dose estimation, patient image quality estimation, and introduction to IndoCT and IndoQCT software, and conclusion. This is the introduction. The use of CT scan has increased dramatically over the last 2 decades in many countries because the CT provides high quality images with very fast acquisition time, as we know. And this is the contributed collective dose, although even the CT only about 10%, but the collective dose is around 60%. Report based on the UNSCARE in 2021. And this is the dose and the rates of the CT. The CT dose values are mostly in the range of the natural background radiation and well known. It is around 10 millisievert. We know that the race is certainly very low, and the model described the base of this race is the LNT model, linear no threshold model, meaning that the risk of the cancer increase with the increasing dose. So the CT optimization is needed and is very important. In the dose optimization, we follow the principle of LRA, meaning that the image quality should have good image quality to accurately diagnose the patient first. And this image should be obtained with the smallest possible dose. So the first one is about the image quality, not the dose. With the very good image quality, and then we found this image with the scan with the smallest possible dose. To measure the dose and image quality, we can use the phantom, just like this one, phantom for measuring image quality, such as the AIPM CT performance phantom or RCR phantom, and also CTDI phantom for measuring the dose. It is very well known and very easy to do in the clinical setting. But we know that the image quality and dose measurement using the phantom with the standard size only good for controllable variable. And we know that the dose and also image quality are affected by 2 variables, controllable variable and uncontrollable variable. The controllable variables such as the tube current, tube voltage, rotation time, pitch/thickness, field of view, and so on. And the uncontrollable variables such as the patient size, patient composition, scan part of the body, clinical indication, and so on. So it is very complicated to measure the dose and image quality in the patient, because the image quality and dose not only affected by the controllable variable, but also affected by the uncontrollable variable. So this is the image from the book of Professor Ihsan Sameh. Measuring the image quality and also the dose can be done by using the simple phantom, controllable experiment to the clinical realism. We know that the measurement of image quality and dose using the simple phantom it is good for quality control. But for the dose optimization, it is very good if we can measure the image quality and dose using the image of the patient. But measuring the image quality and also the dose directly from the image quality is very challenging. But there is so many variables influence to the dose and also image quality. Estimation of the patient from the patient image for the dose, there is the available metric, the SSDE, size-specific dose estimate. The SSDE is introduced as metric for characterizing the dose received in the patient, and it can be measured directly in the patient image. And the image quality, as we mentioned earlier, an ideal approach to optimize and monitor the CT protocol is to directly evaluate the level of image quality in clinical image with specific tasks. So we move to the second talk about the patient dose estimation. Until now, the output dose of CT is characterized by using the CTDI, CT dose index, and its derivative, such as the CTAW, CTA volume, DLP, dose length product, and so on. And these metrics are used widely worldwide. We know that the CTDI and its derivative, it is used for many aspects in CT, for the quality assurance, accreditation purposes, dose optimization, developing diagnostic reference level, and so on. But we know that the CTDI is not the metric for estimating the patient dose. It is only a metric for the output dose. As we already mentioned, that the dose of the patient is not only affected by the output factor, but also influenced by the characteristic of the patient. So the CT dose index and patient dose, they are not the same thing. So in the CT, there is metrics for output dose and patient dose. The output dose using the CT volume and its derivative, and it's depend on the key VMAS, pitch, rotation time, slice thickness, and so on. And patient dose depend on the patient dose and patient characteristics, such as the size and so on. So we know that the image, the dose received by the patient is strongly depend on the patient size. We can see in this picture, if patients scan with the similar output dose, but the patient having the very small size, the dose will be very high. But if the patient is larger, the dose will be very low, like this. So in the 2011, APM issued the report to 2004 dealing with this issue and introduced the new metric, size-specific dose estimate. And all of you can download this report from the APM website. Basically very easy to estimate the patient dose. It is based on the previous metric, CT volume. The CT volume is it is the output dose, and then normalize by using the coefficient, by using the size of the patient. So to measure the SSD is very simple. CT volume multiplied by the F. F is the normalized factor as function of the diameter of the patient. There are so many patient diameter based on the geometrical size. We can also estimate the patient size by using the weight and BMI and age. And by using the geometrical size, we can use the lateral diameter, AB diameter, and also using the effective diameter. And the best one to estimate the patient diameter using the combination, the geometrical size and also attenuation factor using the water equivalent diameter. This is the the effective diameter, it is very easy to calculate the effective diameter using this equation. If we have the diameter in the lateral direction and also in the AP direction, we can very easy to calculate the effective diameter. And this is the equation to measure the water equivalent diameter. It is rather very complicated, because if we want to measure the diameter, we should know the composition of the patient. And by using this equation, we measure the pixel values, and then we average and we calculate that. And then we, using this equation, we get the water equivalent diameter. Basically, in the IUPAP report number 2020, we can use the ROI, region of interest, using the circular shape. But by using this circular shape, we can include also the table of the patient like this. It is better if we measure the water equivalent diameter using the segmentation fitted to the patient border. And we can and we also develop the software to calculate the DW, water equivalent diameter, automatically using the software. It is very easy to do. This is the patient dose estimation. And now we move to the patient image quality estimation. And in this occasion, I only mention about explain the two parameters, noise and also the spatial resolution, with the metric of the MTF, modulation transfer function. Okay, what is the noise? The noise is the fluctuation due to the quantum fluctuation, quantum noise, and also the electronic noise. And fluctuation due to the anatomical variation is not considered as the noise. So basically, it is easy to measure the noise from the clinical image by using the subtraction method. If we have the two images, we can subtract the two images and we get the result like this. This is only the noise. And then after that, we can use the ROI and we measure the noise. Basically very easy to do, but in fact, it is also rather difficult to do in the clinical setting, especially for the for the busy center. So this is the first trial to measure the noise from the clinical image, done by Professor Christiansen and his colleagues. Basically, to measure the noise, to measure the noise from the clinical image, we should measure first the noise map or SD map, standard deviation map. For example, in the soft tissue. Actually, we can also measure the noise in the fat tissue, in the soft tissue, and the bone. But because, for example, in our abdomen, there are many soft tissue, we can only measure the noise based on the soft tissue. For this purpose, we use the segmentation from the 0 to 100 Huntsville unit. And then we make the standard deviation map like this. After we get the standard deviation map, and then we develop the histogram from this deviation map. And from this histogram, we get the peak of the histogram, and we get the SD like this in the peaks. So this SD, standard deviation, is considered as the noise, global noise index. This is the how to create the noise map. So we use the kernel with the specific size. It can be 7, 9, or 11, and so on. And then we move the kernel and calculate the SD. And we do that at every point within the image. and then we get the standard deviation map. And after that, we develop the histogram. And from the histogram, we obtain the global noise index. And this is the result. The global noise level, global noise index, compared to the subtraction method, we can see that the result is very similar. So this method can consider very good to measure the noise directly from the patient image. And this is another method, because the previous one is only good for the abdomen. Maybe we can ask, can we measure the noise directly from the patient? For example, from the head image or from the chest image? Yes, it can be. But maybe in the chest image, the soft tissue is very limited. So this is another method proposed by the Professor Marcus and his college. So in this method, they propose to measure the noise not within the patient image, but from the air outside the patient. So we can see and we understand that the air is the homogeneous region. And so from this region, we can also measure the noise. This is the result. This is the method proposed by the Professor Marcus. Previously, the measurement done within the image, the patient image, and this method measure the noise outside the patient image, like this, in the air outside of the patient image. And then we also get the SD map, and also we obtain the histogram, and we get the global noise index. And this is the result. So there is the strong correlation with the GNI, global noise index, within the patient image and outside the patient image. So based on this result, we can also estimate the noise from the air outside the patient image. This is the result. The GNI in the air with the standard deviation in the liver. We can see the linear correlation between both. This is the noise measurement from the patient image. And the second one
Choi,
is
can you speed up a bit, please?
Okay, thank you. And this is
please speed up.
Okay, thank you, Professor. This is for measure the MTF. Also can be done from the patient. Actually, in this method, we measure in the border of the patient's skin, and we get the ESF, edge spread function. By using the edge spread function, and then we can get the point spread function, and then we using the full transformation, we can also get the MTF also. This is, but using this method is very challenging. But actually, we can do the MTF measurement using this method. This is the result. The MTF automatically measured on the patient image. And now we will introduce my software, Indocity and IndoQCity software. This is the website for download the Indocity and also IndoQCity software. This is the algorithm, how the Indocity measure automatically the dose as SDA from the patient image. This is the graphical user interface of the Indocity. This is the example how to measure the SDE in every slice. And this is the IndoQCity. Basically, the IndoQCity is software for evaluating the image quality of the image. Basically, the image quality can be measured from the many phantom, such as the APM-CT phantom, RCR-CT phantom, CAT phantom, GE phantom, Canon phantom, and so on. And also using this software, we can also measure the image quality directly from the patient images. Yeah, this is the graphical user interface of the IndoQCity. This is the example how to measure the noise directly from the image of the patient. This is the example how to assess the noise level and also the dose directly from the patient. This is the example. And we can measure be further analyzed and compared with the expert radiologists for the evaluation. Again, this is the conclusion. The ideal approach to optimize CT protocol is to directly evaluate the level of image quality and also the dose. And IndoCT and also IndoQCT are tools that can be used to automatically measure the CT dose and image quality from clinical patient images. However, the both software still have many limitations and need improvement. Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Thank you very much, Choirul, for your excellent talk, particularly the innovation of your software, the Indo QCT. A couple of questions been asked on the proton. I think Hoong has replied in written. That is good. One question that came to Dr. Choirul, how to select the diameter D to calculate SSDE?
Yeah. Basically, the diameter can be selected from the middle image in the z-axis. But if we want to get the more accurate result, we can measure the diameter from the all images along the z-axis. And I think by using such as the IndoCT, we maybe only takes less than 20 seconds, I think. Thank you.
Okay, thank you. Now, it's an interesting question on your IndoCT expected. Would you expect IndoQCT to be operated from the center where the scans are taking place or from some remote office as an independent QA tool?
Yeah, thank you very much. And now the IndoCT and also IndoQCT still have the limitation. And now IndoCT and IndoQCT can be operated with the standalone computer. So we can install the software in the computer and we can open the images and then we can calculate automatically using IndoCT and IndoQCT. Maybe in the next we can also can redevelop, so can we measure the image quality remotely in the future, inshallah.
Yeah, and of course, everyone interested. This software free.
Yeah, yeah. Until now, the software is free. But for IndoQCT, need the ID and also the key. So if you want to install the IndoCT and the QCT, please send the email to me and I will give you the key and ID. Thank you.
Okay, thank you. Everyone interested in getting a free software. Now, let's go back to the question to Hoong on the proton. We are very interested about the dispersion, right? It's fairly new. They're asking if there's a difference between the synchrotron and cyclotron systems. Which one is more dispersion and how does your system compare to the others?
Okay. So this one is, I mean, many different ways to answer this. So a lot of this, so we work with Hitachi, right? The dispersion varies between different sites and it depends on the engineer tuning the systems. And so, so that's one thing. And second is between cyclotron and synchrotron, at least for cyclotron, it's not reported. And a lot of these things got to do with the way they extract the proton beam. So I think it's very different. So there's a chance that they might not have noticed it. But one thing that we got was after we reported this, several sites actually, emailed us and said, hey, actually we have noticed this problem for the longest time. And like they kept this quiet and they have never reported anything about it. And now after we reported it, and then they said, okay, so this is actually the source of the problem. So it could be that sometimes they have this problem, but it's not reported. So at least that's my answer to this question.
Now, do all the proton centers perform this dispersion
No,
as
they
part of
don't.
the QA?
No, they don't. So this is something that's not the norms. So that's why we recommend it as it's good to do it once for commissioning at least. But as of now, that is not the norm. Most centers will not have measurement that measures the dispersion. Yes.
What happens if the dispersion exceeds the limit? how is the implication on the clinical outcome?
So if it's actually very, very high, then chances are you get a lot of you might get the dose that's reported is delivered to a patient might not fully agree with what is shown on the TPS. So that's what you might expect. But at the tumor, because it's actually at the SOBP region, the spot size is actually pretty large. So the spot drift doesn't really matter that much. But it could mean that at the plateau, at the surface dose, all these things, we might get all the estimation all wrong. So that will be a clinical impact. Not in the tumor control, but probably more in the normal tissue complication kind of area. Toxicity side where we might get it wrong if we look at the dispersion rate. Yes.
That's very interesting. Yeah, I'm sure those who are listening attentively remember the physics of dispersion, right? Particularly, you learn about light, isn't it? The dispersion through the prism, right, of different wavelength. I think quite analogous to that, right? To understand that part, the equation. Thanks very much, Hong Chi, for explaining. And there's one question just came in for Dr. Choroy. Can you read that? It say, I'd like to ask Professor Choroy, I'm building a program for organ clustering based on chest X-ray. Are there any suggestions or method that I can use? Can I use a method like k-means clustering? Then how to explain the relationship between clustering results and organ type based on medical physics principles?
Yeah, basically by using the K-mean factor, we can also measure and classify the organ in our body, and we can also basically you can send me email and I will explain you more deeply about the K-mean clustering because it is very difficult to explain more detail in this very short occasion.
Yeah, probably you need a whiteboard as well to illustrate. Okay, there's a very good question. Now, we can entertain one or two more questions. Please send in your questions before we end our session this evening, this afternoon. You can always send an email to both of our speakers. Any more? One or two last minute questions. There's one asking about, can we do volume estimation in nuclear medicine images from this software? There's your IndoQCT.
Yeah, thank you very much. Actually, the IndoQCT and IndoCT is only for the CT images. We can also measure the image quality from the MR images, but of course, without the automatic method. But it can do it, but without the automatic method. For the automatic method, only for the CT images.
Yeah, thanks for the explanation. One question. Are they open source?
Yeah,
for IndoCity.
Basically you can use the IndoCity and IndoQCT for free. And if you need the ID and also password, please contact me. Please send an email to me.
Okay, I think with that, I would like to thank, first of all, our two speakers, Dr. Hong Chi Tan and Dr. Choirul Anam, for the excellent presentations. They are the awardees of the IUPAP Early Career Scientist for this year, 2023. Right? And we congratulate them for receiving such great honors. Also, both of them happen to be from Southeast Asia, from Singapore and Indonesia. Excellent. I also like to thank the audience. We have more than 1,100, excellent attendance, 1,100 over who have attended, and many have asked lots of questions. You can go to the Q&A. Some have been answered by Dr. Tan. You can continue to engage with them through email. I also like to thank the organizer, Dr. Adelina Stoeva, for organizing this event and publicizing that. Okay, and this session will have been recorded and will be uploaded as YouTube under the IOMP. Thank you for all of you, and have a good day, good evening, and keep safe. Bye-bye.